Hello guys, this is Team Shake a Leg from Subject Computer Science 90054, the University of Melbourne. In this video, we're going to present our design and implementations for the Artificial Intelligence contest, Pac-Man Capture the Flag. The contest is a multiplayer variant of Pac-Man, and the figure shows a sample layout in the contest. Two teams, where two agents on each team will compete in one of many layouts. As you can see, the layout is split into two halves, and each team is going to eat the food on the other side while trying to defend food on the home side. An agent is a ghost on the home side, but will transform to Pac-Man when crossing into the away side. A Pac-Man can be eaten by a ghost and will be sent back to the starting position. But there could be capsules. Well, the opponent ghost will be scared if a Pac-Man gets a capsule. A Pac-Man can eat scared ghosts. The team will win if they eat all but two of the opponent's food, or lead in the scores when the time limit is achieved. We mainly used two techniques for this contest, which are A-star search and SARSA. We're now gonna briefly explain the theories, our motivations, and the applications of these techniques. A-star is a graph traversal and path search algorithm. It starts from a specific starting node of a graph, and it aims to find the path to the given goal node, while having the smallest cost. So it's guaranteed to give an optimal decision if there is one. At each iteration, A-star needs to determine which of the paths to extend. It does so based on the cost of the path and the estimate of the cost required to extend the path all the way to the goal. Well, specifically, A-star selects a path that minimizes Fn, and which equals to Gn plus Hn, where Gn is the cost of the path and Hn the heuristic function, which estimates the cost of the cheapest path. A-star search is commonly used to compute the moves of NPCs in many games, so it's well suited to this project. The sub-goals when chasing the win can be classified as some of the search problems, like search for food, search for Pac-Man, and search for a safe place, etc. So A-star naturally became a choice. Okay, let's now take a look at the implementation of A-star. In the search problem part, we designed many problem types like food, capsule, Pac-Man, ghost, etc. So we gave a search problem to an agent, and the agent will use A-star search to solve the problem and further make a decision on where to move. For example, if we will want an agent to attack, we will assign problem food to the agent. Or if an agent is being chased by a ghost, we'll assign a problem safe position to the agent. Well, safe position can be either the other side of the boundary or where a capsule located. This is the main search function, and this is the heuristic. And we also use the idea of classical planning as a guide to design the logic in the structure of the search actions, which saves computation time from searching paths to unrealistic or unreasonable targets. As you can see, these are the actions and related conditions. This part of the code makes function calls and also makes sure the correct priority.
Hi, I'm Zian, and now talk about SARSA, which is an on-policy learning algorithm. As a SARSA agent interacts with the environment and updates a policy based on the actions taken. The algorithm is used in the reinforcement learning area of machine learning. Let's look at the algorithm closely. This is the equation used for updating the Q-value. SARSA is very similar to an off-policy reinforcement learning algorithm Q-learning. However, SARSA uses the actual next action to update the Q-value, while Q-learning uses the maximum Q-value. Therefore, we chose SARSA over Q-learning due to lack of training sets, because Q-learning is an off-policy learning, which is more appropriate when we have the luxury of training our agent offline before it's put into operation. However, SARSA is an on-policy learning, which is more appropriate when we want to optimize the behavior of an agent who learns while operating in its environment. And this is exactly what we need for an online Pac-Man contest. Let's see how the algorithm is applied practically. The reward in the formula is assigned different values based on the conditions. This is an example of our setting. Negative rewards lower the Q-value, such as the reward of a ghost, and the positive rewards lower the Q-value, such as the reward of a capsule or food dot. More specific, the reward of a capsule is larger than the reward of a food dot, means that an agent is more likely to eat a capsule than the food dot if it has a choice.
Now let me show you our design choice. Our offensive agents can search for food, search for capsules, dodge ghosts, and defend when necessary. And our defensive agent can chase a Pac-Man, protect capsules, and go to attack when necessary.
Let's see how can we improve our project in the future. The first step is to solve the remaining challenges which we just mentioned, and the second step is to improve the implementation of the techniques, such as reducing the time complexity of A-star algorithm with better data structures and optimizing the heuristic functions to achieve better actions. At the end, we can try some other techniques such as Monte Carlo tree search and deep Q learning.
Okay, now let me give you a live demo. So this is my team.py, and in function create team, we have one agent, attacker A star, and another agent, defender salsa. And these are the implementations. These are the arguments. We are the red team, so let's just run it. This is it. Thank you so much for watching, and we are team Shake a Leg.